Morning. Welcome back to chemistry. It's Thursday, April 23rd, and we are going to go over a few questions to start us off that follow up to our calorimetry stuff that we were doing earlier this week. There is the calorimetry lab due on Sunday, which is mainly going through and doing the calculations that are given to us in the data section of the lab. And I have some office hours later today, Thursday, at 1, and then on Friday from 9 to 11, and then again from 2 to 3, I believe. So you can pop in and ask questions about that. And warm-up number 2, however, is pretty closely related to the first calculation you're going to have to do in the lab. So hopefully this helps as well. So let's go through. I had this question opened up on Google Classroom, so you can submit your answers. And I got a few responses to help before we got started to help gauge how we're doing. And it looks like there were definitely some correct answers, but I want to make sure to go through it to help the people that need a second look at this. So let's take a look. The first question brings up a situation where you have this metal, this unknown metal, and where you have a mass of the metal. So I'm just going to take some of the information from the question and write down which variable it represents. When we're doing heat transfer reactions or heat absorption or heat release, we have the Q equals MC delta T equation, which is our algebra equation that we're using to guide us. So a 50-gram sample, that's going to be our mass. I'll write M equals 50 grams, is heated with 800 joules. Now, the unit of joules, that's a heat energy, and our variable Q actually represents heat energy. So Q in this case is going to equal 800 joules, capital J. And then if the temperature of the metal increases by 41.6 degrees. Now there's only one temperature given, and so that's considered the change in temperature. Sometimes we have a final temperature and initial temperature that we have to deal with, but in this case the overall delta T is 41.6 degrees. What is the identity of the unknown metal? So looking at this question and the given information, the only variable that we don't know is this specific heat value, which is C. And I've given some C values in the top right corner. So we're going to take these values, plug them in, and solve for C. Once we solve for C, we can match it up to an unknown metal. One of the techniques I like to do is actually rearrange this equation as the letters before I substitute, and it minimizes some mistakes. So I can divide both sides by M delta T, M delta T. If I divide both sides by M delta T, then I have C by itself on one side of the equal sign. On the other side, we're taking Q and dividing by mass and delta T. And then I'll just be able to substitute from there. 800 on top for the joules, the mass is 50, and the overall change in temperature was at 41.6. Once I have this set up, I can just go to my calculator, 800 divided by 50. I like to hit enter first, and that's backwards, but divide by 50 first, and then I can hit equals, then I can hit divide again, 41.6. And I get a value about 0.3846, etc. in my calculator, and we can look at it, and this value is really close to the one given for copper. So the correct answer for this one would be copper. We can use the specific heat to identify an unknown metal. And this is really the goal for our lab, is identifying the unknown metal by finding a specific heat value. Now in the lab, we have a little bit more information. There's a calculation we have to do to get the joules first. So it's kind of split into two different parts. So let's go to our second warm-up question. A 77.5 gram sample, so already we have a mass value, of an unknown solid is heated to a temperature. Sometimes when I read through, I'm not really too focused on what the numbers actually are, just what variables they represent. So we have a mass of a sample of a solid, and it is heated to a temperature and placed into a calorimeter, which is that device that we use to transfer heat between more than one substance. In the calorimeter, we have a mass of water and we have a temperature of water. If the final temperature of both substances reaches that final temperature of 26.2, what is the specific heat of the solid? So I chose this one because it's very similar to the setup we had for the lab. And what I want to do is split this into a couple different parts. First of all, we have two different substances, so we can address each of them separately. With the unknown solid, I'll just put that off to the left, and then we have information about our water source. And the idea is we are taking the water in the container and putting the solid and mixing them, and once they mix, they're exchanging heat. And the amount of heat exchanged between both of them can be measured using the Q equals MC delta T equation. One is going to be losing heat, and the other one's going to be gaining heat. And I can write a Q equals MC delta T for each of them separately. How much heat is transferred from the solid to the water, or vice versa. Now in this case, I can make a prediction about which one's losing heat and which one's gaining heat. As we write out the variables that are given, we can kind of see what's missing. So the unknown solid is heated to 62.5 degrees before it's placed into the container. So that's going to be the initial temperature of the solid, 62.5 degrees Celsius. And then it says the final temperature of both the solid sample and the water reaches that 26.2. So after they're mixed, there's this time in between where they're both reaching the same temperature, they're exchanging heat, and then eventually they both reach the same temperature. That's this thermal equilibrium situation. So I can say the final temperature should be the same for both of them. So the temperature final is going to be 26.2 degrees Celsius for the solid. And then for water, water started at a little bit lower temperature. The initial temperature for water is 23.3. And then the final temperature, again, they both reach the same final temperature. So you can say that 26.2 is the final temperature for both. We have a mass value of the sample, the solid sample, 77.5. And we have a mass of the water. So a lot of this is just organizing the given information. We do have a C value for water, which is 4.18, and this is usually a given value. And before I given like 4.2, which is a rounded number, 4.18 is a little bit more specific to 3 significant figures. So we have all this information, and now we just need to organize it. The unknown is our C value of water. What is the specific, or sorry, the C value of the solid? What is the specific heat? So to make this a little bit easier, I break this down into 2 separate calculations. I'm going to use the Q equals MC delta T equation for water first and figure out how much heat was actually absorbed by the water. And I'm going to do this in a separate color. So I'm going to plug all these values in for water and figure out the heat absorbed by the water. We have 93 grams, the specific heat value of water, which I'm using 4.18. And then the delta T for the water is going to be T final minus T initial. So I'm going to take the final temperature, 26.2, and subtract from it the initial temperature, 23.3. And this is a way of solving for delta T, where you're doing T final minus T initial. So I'll, in my calculator, once I have this all set up, I'm going to subtract those numbers first because they're inside the parentheses. Hit enter, get a value for that, then I'll multiply it by the specific heat, and then I'll multiply it by the mass value. So these numbers are in joules, so this number actually looks pretty big, but this Q value is 1,100, and I'm just going to round to 130. Technically, you can leave it in your calculator and round at the very end, because we're going to use this number in a later calculation, but this is fine if you round right now. We're just getting close values. So this is heat absorbed by the water. And I'm able to say that because water is starting at a lower temperature and the temperature is going up. Let me clear this really quick and draw something out. We know that if we do a little thermometer scale, here's my thermometer. Water is starting at 23.3 degrees Celsius. And the metal is starting at 62.5 degrees Celsius. And then they eventually reach the same temperature, 26.2. Not really drawn to scale, but that's okay. The temperature of the metal is going down. So it's losing energy. It's giving its energy away. The metal is transferring its energy into the water. And when the water absorbs that energy, its temperature goes up. And to make a connection to endothermic and exothermic, when the metal is transferring energy away and losing energy, that's an exothermic process. And exothermic processes are going to have negative energy values, negative Q values, a loss in energy. Whereas the water value, it's going to be endothermic. It's going to be absorbing that energy as its temperature is increasing. And endothermic processes have a gain in heat energy, which is a positive Q value. And this part is really important because these Q values, the energy loss and the energy gain, these are actually going to be equal to each other. Equal and opposite. So if we get a Q value for water, we can change that into a Q value for the metal, just as long as we change the sign. So the Q value for the water is a positive 1,130 joules from our calculation we just did. And then that equals the Q value for the metal, how much energy the metal must have lost. We're just going to change the sign. And you're going to do this in your lab report as well. Pretty much the exact same process. So now we have a Q value of the metal that we got from the Q value from the water. Equal and opposite. And this goes back to one of the relationships that I lectured about. The negative Q of the hot substance equals the positive Q of the cold substance. This applies when you have two substances, you put them into contact, and they exchange heat between each other. So let's go back and solve for the Q value, or the C value of the metal, MC delta T. This is going to be for the metal now, where we are using the answer from our first calculation as the Q value. Because it's negative, that's going to make sure that the negatives cancel out. We don't want negative values for our C value. Specific heat values have to be positive. So we'll see how this negative gets handled. We have the 77.5 grams of the metal. The C value for the metal is what we're solving for, the specific heat. And then the delta T is going to be the T final minus T initial. The final temperature it reached was 26.2, and the initial temperature was 62.5. So just to specify which one is the final minus initial. Anytime you have a delta T and you have two different temperatures, you can solve for that delta T by rewriting it as final minus initial. And here, now we have everything plugged in correctly. I'm going to go ahead and subtract the temperatures really quick. Because it's losing, the temperature is going down and it's losing energy, this delta T is a negative 36.3. So there's that negative, and the negatives are going to cancel out. So that negative from the Q is important to cancel out the negative from the delta T. And then we can finish this and solve for C by dividing both sides by what C is being multiplied. I'm going to divide both sides by 77.5 and both sides by negative 36.3. So I'll get that on the left side. So 1,130 divided by 77.5, and again divided by 36.3. of that, negatives cancels out, and my final answer is 0.402, and the units will be joules per grams degrees Celsius. And I had more than one person submit that 0.4 was the answer. It looks like the majority of us are getting that, which is great. Hopefully, if you did not get 0.4 the first time, you caught where you got lost, or maybe you figure out, like, you get to a point where you just don't know what the next step is, or you just need help starting the question. Hopefully watching this helped you out with that. So continuing on, one of the things I wanted to talk about today was heat convection, which is a way of relating the flow of heat energy to something that we experience more often in real life, or that was might be a little bit more familiar to us. Instead of talking about chemical energy change or heat transfer, we're going to talk about heat transfer with the Earth. And when I think about this, the first things I think about is plate tectonics, and under the crust, we've got the upper layers of the mantle that are like molten lava, magma under the ground churning around, and there's a lot of movement under the surface. So some things that I want us to think about as we are going through some questions that we can answer are, how does the flow of heat affect Earth systems? And how can I use the concept of convection to explain how some machines transfer heat? That should not be an apostrophe. I'm going to fix that before I go crazy. There we go. So let's start with the Earth. A little bit of a review. The Earth is broken into several layers. We have the crust, which is shown as this outer layer. And then we have this, just underneath the crust, there's broken into several parts, but the main word for this would be the mantle. So we have the crust, we have the mantle, which we'll talk about the different specifics of the mantle. And then we have the core. We have the inner core, and we have the outer core. So there's a lot of heat transfer between these layers because they're at different temperatures. Anytime you have things near each other at different temperatures, there's going to be transfer of energy, especially with fluids. When liquids are near each other, and different materials of liquids at different temperatures, they rise and fall based on differences in temperature, which ultimately affect their density. Temperature and density have a close relationship to each other. So pulling up a couple images, this one is a much more detailed look at the cross section of the Earth. You can see some distances. You can see the radius of the Earth being just over 6,000 kilometers. And then the picture at the top right, where it's breaking the crust down into several different layers. You got different types of crust. You've got oceanic crust and continental crust. Those different crusts have different densities because they're made of different material. And then under the crust, you've got this large section called the mantle, and the mantle is broken down in different parts, which we'll get into after this. And then the inner and outer core. The outer core is liquid, and the inner core is solid. We do have a solid nickel iron core. And then the outer layer, the outer core is different material and very, very hot, but it's able to exist in the more of the liquid phase, and it's allowed to flow. And anytime metals can flow and move around, specific metals, they create a magnetic field. So this churning molten metal core is what creates our magnetic field. And without that, we wouldn't be able to resist the extreme conditions of space. Our planet would be bombarded with cosmic rays and we wouldn't really be able to survive. It's our molten core that creates this magnetic field that protects us from a lot of this cosmic radiation that would harm us. In general, as we get closer and closer to the core, as we're increasing with depth, the temperature is increasing. So there's a little caption on the bottom left. As we get closer and closer to the center, the temperature is going to be increasing. And that's going to be changing how these fluids interact with each other and move around. To get a little bit more detail, just to list it out, we got the crust. The mantle is broken into two sections called the lithosphere and the asthenosphere. The lithosphere is just under the crust, and the asthenosphere is below the lithosphere. The asthenosphere is this molten magma section that is constantly churning around, which is largely of interest to me because hot molten liquids get to move and create these convection currents that I wanted to mainly focus on in this section. The core is important as well, but we're not going to focus on the core too much other than the fact that the outer core is a churning liquid layer as well. What I want to focus more on is this asthenosphere layer, which is going to have a lot of our convection currents that's going to ultimately affect our plate tectonic movements. Imagine you got a little bit of this in middle school science, so if it sounds familiar, that's good. So how does convection work? The idea is, even within a pot of water, and you're heating this pot of water, there's different layers of temperature. The part of the water that's closest to the burner is going to get warmer, and warm water is less dense than cold water. And so when you heat up water, the density slightly changes, and the less dense water is going to rise, and the colder water is more dense, and it's going to want to fall. And they start replacing each other. And there's a quick video I wanted to watch, and it's only a couple minutes, that is a really cool experiment that you could actually try at home with some food coloring and a reasonably sized fish tank. So let's check this out.
Hey kids! Are you in elementary school?
Get through this ad first.
Get ready for one of the most hypnotic things you'll ever see in a science class. Have you heard that heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. Do you see it? The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it. As it goes out to the edges, it starts to get cool.
So only the middle cup is a hot water cup. The outer cups are there just to support it and have the same height. But we're going to start seeing this circular convection current. And I want you to start thinking of how this would function underneath the surface. If there's a layer of molten magma underneath our surface, the lower part is the hottest because that's the closest to the core. And the crust would be up atop, closest to us. There we are at our little computers. And underneath it, there's this constant churning layer of magma.
And cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are called convection currents, and you see them moving here in two big ovals. They're one of the major things that drive ocean currents, especially in the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe, some of them taking 1,000 years to complete their course. Understanding convection currents will help you get a grip on weather systems and the movement of Earth's continents over the eons, and even the workings of a lava lamp. If you want to try this for yourself, click on this link for all the directions you'll need. Thanks for watching.
All right, let's jump back to it. So basically you just need hot water, fish tank, food coloring. You need to put it in the right spot. So there's a part where he explains that. But I thought it was a really cool experiment if you have the stuff for it. A really cool experiment you can do at home. So I was kind of drawing this picture on the video, but this is an image of the crust at the very top, and then underneath you have the layers of the mantle, specifically the asthenosphere, which is that heated material, molten and magma. And you can see how it comes up, breaks to the surface, or starts recycling and churning around over and over and over again. And this is the fundamental idea of plate tectonics. A lot of this sparked based on observations made a while ago, where the idea is plates move so slow that it's hard, you can't really see it in real time. Even over a lifespan, it's very minimal. So there had to be observations based on the continents being separated, but having similar landforms. And once mapping became really big, they started seeing that these continents fit together like a puzzle piece. And they didn't know how they move, but they just, based on observations, theorized that the plates do move. And it wasn't until later with some better scientific instruments that they were able to determine how they moved after that. Current maps are breaking the planet into plates. So here's just a view of the plates. And these are just sections of crust that are joined. And you can see that our continent, hopefully you can find our continent on this map, but we are about right here. And you can see the North American plate is sitting, North America sits right in the middle of North American plate. And we get a little bit of Asia in there. We've got Greenland. And then this yellow plate in the middle, there's no continents there. That's just the Pacific Ocean. So the entire Pacific Ocean is, well, not the entire, but most of the Pacific Ocean is on this plate. And then there's a lot of movement. The big part that we feel is right here. There's a lot of movement where the Pacific plate meets the North American plate. And California is right on that border. In fact, the whole western coast is right on that border. And it's called the Ring of Fire. Yep. I got it in chat, someone was saying Ring of Fire. Yeah, we're right on the Ring of Fire. So we get a lot of volcanic activity that's responsible for our mountain ranges on the west coast, and a lot of our earthquakes as well. Specific ways that these plates interact create this rubbing effect. And when these plates, when there's a large jolt in this, the friction between these plates, we feel it as earthquakes. There are constantly earthquakes happening, just a lot of them we can't feel. An interesting about this, those that have been on the East Coast, take a look where the East Coast lies. Think of the topography of the West Coast versus the East Coast. Over here, we've got large mountain ranges, beautiful um, skiing resorts, very rocky. Where on the East Coast, it's rather flat, especially even the middle America, it's very flat. Unless you have these um, specific ranges, like there's like micro tectonic activities where you can get these jolts of mountain ranges. This doesn't show all of those, it's just the primary plates. But on the East Coast, it's rather flat because it's not sitting on any plate boundaries. Sorry, smacked my keyboard. One of the other places that gets a lot of activity is over in India. And there's a very unique interaction over here that creates the highest mountain range in the world, the Himalayas. On this one mentions the Ring of Fire. This is the most active volcanic range in the world, right around this Ring of Fire. And all those little, this is not the best quality picture, but all those red dots show major volcanoes. And you can see in California, we have some right there. Mount Shasta is one of the closer dormant volcanoes. When I was young, before you guys were born, I have relatives that live up near Mount Shasta. When I was young, I remember being up there and smoke coming out of Mount Shasta. And it was a really weird, surreal experience. It didn't erupt completely, but it was just, it was smoking for the whole day. It was pretty cool. So what this does and what these convection currents do, this difference in temperature and density, creating these large currents on the ground, it's moving these plates around. And ultimately it's throwing these plates together. And so they crash into each other like bumper cars, or it pushes them away from each other when these heat plumes break the surface. So this left example is where these heat plumes break the surface in weak spots and actually push the crust away from each other in both directions. You don't need to know really what the names of these boundaries are. It's just to create some extra depth to what I'm saying. But these divergent boundaries are largely happening underneath the ocean. We can't see these. In the Atlantic Ocean, there's one of the biggest mountain ranges in the entire world. It's just buried underneath water. In World War II, when submarines became popular, they started using sonar to detect enemy submarines. And one of the really weird observations that happened is they thought the bottom of the oceans were all flat, but they kept getting back this data of these enormous mountain ranges, these enormous changes in elevation underwater. And they, out of all this war technology, they made a huge discovery about the nature of the convection currents, the nature of the plates, and what was actually underneath the Atlantic Ocean. So the mid-Atlantic ridge is this enormous mountain range that spans the entire Atlantic Ocean from north to south, pretty much right in the middle of it. And so this hot magma breaks the surface and spreads outward and carries the crust, the oceanic crust, I'm drawing on the board if you can see, carries this crust towards the continents. Now, oceanic crust is more dense. So when it hits the oceanic crust, hits the continent, it folds and one goes up, the other goes down. The more dense substance, the water-rich oceanic crust is really heavy and it falls back down underneath the surface. There's actually a huge recycling effect with our crust. If we look at the oceanic crust, it's very young. There's not a whole lot of crust that's older than a couple million years. The oceanic crust is constantly recycling, which created some issues when we were trying to figure out the age of the Earth. If we wanted to figure out the age of the Earth, we had to dig up rocks that were really, really old, billions of years old. And so we had to find areas on the crust that really have never been recycled through all the time of the volcanic activity that would melt down these rocks and re-solidify them. Anytime the rocks melt down and re-solidifies, it kind of resets the age of that rock. We needed to find rock that hasn't really been melted down at all. And so we found really old samples on the crust that help give us an idea of how old the Earth is. The first billion years of the Earth was very chaotic. Huge amounts of volcanic activity. There wasn't an atmospheric layer. There wasn't any oxygen. So I am fascinated by this stuff. More space science, the earth science aspects of this are really interesting. And I wanted to make some connection to all this chemistry that we're learning about heat and transfer of heat energy and difference in temperatures and how those affect each other. And so it has a very real effect on the convection currents that we experience with our Earth. Something I wasn't going to get into, but there's also differences in temperature in our atmosphere. There's several layers of our atmosphere, and the air currents are also derived by the same phenomena, where there's difference in temperatures in the air, which causes differences in density, and a lot of our air currents are powered by just a difference in temperature. It's fascinating. So what do I want you to do next? I want you to get a little bit of research in, and so I have a short assignment that I'm planning on having you turn in by next week, Sunday. So you have over a week. And I'm asking you to write 2 paragraphs. I want you to write 2 paragraphs and explain why do air conditioners work, or how do air conditioners work. If the goal of an air conditioner is to transfer heat in the air outside of the house and cool down your house, I want you to do a little bit of research and be able to describe how do they work. Now, I don't expect you to be able to build air conditioners or install air conditioners when you're done, but there is a very common piece of machinery in your house. And if you do a little bit of hunting, you can find a how-to on air conditioners and how they function. So first, this weekend's going to be in the 90s, so have fun with that. I want you to, when the next time your air conditioner's on, make some observations. Whatever that entails for you, just make some observations. What's it like inside the house? Go outside, find your air conditioner, what's going on, feel around, and your observations need to be a part of your paragraphs. So the first paragraph could include your observations and your theories behind that, and then start talking about your research and basically explaining how air conditioners work. And then somewhere in your 2 paragraphs, I want you to explain the difference between a condenser and a compressor. These should be some words that pop up in your research, and just have some sort of explanation between a condenser and a compressor. So I plan on having you turning this in through turnitin.com. It's an easy format for me, and through your English classes, you've used this before. So I'm going to be setting that up. If there's any change in this format in the next week and a half, I'll absolutely let you know. I would say at basic, you can be just typing this out on Google Docs. Now, if you are concerned about submitting something digitally, whether it's turnitin.com or emailing it to me, just let me know. Let me know after this weekend, before the day it's due. Let me know, and I'll of course make some accommodations. But we're going to write a couple paragraphs on how air conditioners work. Turnitin.com will let me know if you just copied and pasted paragraphs off the internet. So please write this in your own words. Use quotes, absolutely, just use them correctly. Perhaps on one of my sessions next week, I'll go through how to embed quotes and just an example of taking some information and writing a sentence in your own words that's using information from the internet. So I'm going to put this assignment on Google Classroom later today with the instructions and how to submit it. I'll open up the turnitin.com assignment, and I know we have our lab that's due this Sunday. Those are some calculations that you're finishing up, but I'm giving you this early in case you're finished, and this will be due end of next week on Sunday. Any sort of adjustments that need to be made, I will let you know, but right now that's the plan. Thanks for stopping by. Thanks for watching, and I will see you at either office hours or next week.